Good afternoon and welcome back for part 2 of this mini-series of presentations related to reproducibility of preclinical data. Just as a short reminder, what I told you yesterday in the introduction, multiple studies have now consistently found that more than 50% of published non-clinical findings in biomedicine cannot be reproduced. Looking into potential causes for this, some key issues have been identified, and these include various biases which can occur at the level of study design, study conduct, including data analysis, specifically statistical data analysis, and reporting. And overall, untransparent reporting is another key issue. Yesterday, I mostly talked about study design and study conduct, and today I will mostly talk about data analysis and reporting. In the last few years, various scientific journals have adapted their instructions to authors to promote reproducibility of published papers. And that has occurred in multiple disciplines, from clinical journals with strong science sections, such as the Journals of the American Heart Association, the Journals of the American Physiological Society, Nature, and I was involved as project lead in the revised instructions for the Journals of the American Society for Pharmacology and Experimental Therapeutics. And when these were released in January this year, we published a tutorial on this simultaneously in all three journals, together with my colleagues T.G. Murphy from Emory University in Atlanta and Harvey Motalski, who is a statistician but also the author of the GraphPad Prism software. So the present presentation will be based on these specific recommendations, but they have large overlap with those in other journals. The recommendations focus on data analysis, specifically also statistical data analysis and reporting. They do not focus on design and conduct of studies, and the reason for this is that they can be applied to already existing data sets prior to submission. What you will see in the rest of these presentations are 11 specific recommendations with the underlying rationale, and at the end, 4 practical how-to examples based on real datasets. Recommendation number 1, include quantitative indication of effect sizes in the abstracts. That can be for whatever you consider the most important quantifiable finding of your study. It can be a numerical effect, for example, a difference, a percent change, or a ratio with its 95% confidence interval. It can also be a general description, such as inhibited about half, almost completely eliminated, or approximately tripled. What you should not do is report p-values in the absence of an indicator of effect size. Why do we recommend that? Obviously, it has a different biological implication. If a given variable triples, then let's say a 10% increase, even if both end up having a p-value of less than 0.05. Recommendation number 2, and that is a topic I talked about also in part 1. State which parts, if any, of the study test the hypothesis according to a pre-written protocol, and which parts are more exploratory. A p-value related to a pre-specified hypothesis based on a pre-written protocol has other implication than a descriptive p-value related to data acquired less stringently. So what do I mean by a pre-written protocol? A good study protocol, as finalized before the study starts, includes all key aspects of study design. For example, the hypothesis being tested, the number of groups, the specific intervention, and the sample size per group. The study conduct, for example, whether and how you applied randomization and/or blinding, and data analysis. For example, whether you plan to normalize any data to transform them, for example, expressing mRNA expression data relative to a housekeeping gene, and your choice of statistical tests, and to report whether these decisions were made before the data were viewed. Anything else falls into the exploratory category by default. And as I said yesterday, there's nothing wrong with exploratory research. Exploratory work can lead to highly innovative insight, but should be identified as such. Examples of exploratory studies include the analysis of secondary endpoints in a pre-planned study, results from post-hoc analysis of previously obtained data, or any findings from experiments in which aspects of design, contact, or analysis have been adapted after initial data were viewed. And why this is so important, I discussed in great detail in part 1 of this mini-series. Studies based on a pre-written protocol have a higher prior probability that the hypothesis being tested is true, which leads to a lower false discovery rate. And I will talk in more detail about the false discovery rate later on today. P-values from exploratory studies, however, cannot be interpreted as hypothesis testing, only as descriptive, and they have a surprisingly high chance of not being true. Benefits of studies according to a pre-planned protocol, other than being hypothesis testing studies, are, as explained yesterday, they reduce bias, they protect from p-hacking, and they protect from HARKing, which stands for hypothesizing after results are known. And I'll explain both terms on the next few slides. Something that you may wish to consider is putting your study protocol into a public depository prior to start of doing the study. This is a good way to document that your study really has been pre-planned. Such deposition of the protocol can be under an embargo so that people cannot see what you are doing, which is so exciting. However, once you submit the manuscript, the embargo is lifted and the URL of the deposited protocol can become part of your manuscript. Forums to do this include the examples listed here, which are largely for the US, EU, or Germany. Another option I mentioned yesterday is taking this a step further, registered reports. Basically, you submit your study question in the form of a manuscript introduction and your scientific approach, basically the methods section of the manuscript, to a journal. It gets peer-reviewed like a regular manuscript, but the beauty is you get the decision whether the manuscript, once the study is done, will get accepted before you even start doing the study. The only exceptions are if something goes grossly wrong or if you have major violations of the original protocol which are not well explained. However, the main limitation is that this is more applicable to in vivo than in vitro studies. So what is p-hacking? You have obtained data, do a statistical test, and if the p-value is smaller than 0.05, you go on, report the data, and that's it. However, if the p-value is larger, you go back and invoke one or more of these p-hacking methods. You tweak test parameters, for example, switching from 1 to 2 tail tests or applying pairing. You collect additional replicates, normalize, transform the data. You omit the adjustment for multiple comparisons. You omit outliers or bad replicates. You analyze only a subset. You add or remove treatment groups, change the key response variable, change the control group, or use a different test altogether. All of this may lead to a smaller p-value, but this resulting new p-value no longer tests an hypothesis because you have massaged the data until you got the finding you liked. That has nothing to do with science. HARKing is another way of generating highly biased data. Imagine you've done a study, but the data do not support the original idea underlying the study. For example, the presumed primary parameter has a p-value of greater than 0.05. However, you've also looked into other parameters, and one or more of them have greater effect sizes and smaller p-value. So you now write the manuscript to sound as if the study was designed to test the alternative parameters. Or even worse, you only report on these alternative parameters. Why is this so wrong? The new manuscript implies a high prior probability and thus low false discovery rate, when in reality prior probability for the newly chosen parameters was low, implying a high false positive discovery rate. Moreover, this violates the randomness principle which underlies all statistical tests. Recommendation number 3. Report whether sample size, number of experiments was determined before collecting the data. It's tempting to run a small experiment, and if the p-value is less than 0.05, you stop and report, but if it's more, you add more data. I'll be happy to admit that this is something I've done repeatedly in the 30+ years of my scientific careers, but I have stopped when I realized that this really was wrong. It is actually a form of p-hacking leading to biased results. Why are they biased? The experiments would not have been added if the initial results looked neutral and didn't show a trend. Even if the finding is true, the effect size is likely to be exaggerated. New expanded samples are contaminated by the original findings you liked, so no longer represent a real random sample. Ideally, sample size is based on power calculations, but in experimental biology, this is not always feasible. The most important reason is, in clinical medicine, we have a good idea what is a meaningful minimum effect size. For example, when we test a blood pressure lowering drug. However, in experimental medicine, who has any real understanding whether the expression of a certain gene needs to go up by 10%, 50%, or 200% to be biologically meaningful? There is, of course, an option of adapting sample size. However, even how this is done must be specified before you have viewed any of the data. Recommendation number 4. Provide details about experimental and analytical methods. Ask yourself, how often did you wish to apply a published technique but could not because of lack of information in the published paper? Methods should have enough granularity to allow readers to understand what has been done so that results and conclusions can be evaluated. Of course, they should also be with high granularity to allow others to repeat the study. This, of course, will overall lead to rather lengthy methods parts in manuscripts. However, if too much space is needed, there is always room to put details in an online supplement. Let me give you some examples of what should be in the methods section, which often is not at present. Which steps were taken to avoid bias? For example, did you pre-specify the protocol? Which elements did you pre-specify? Did you apply randomization and/or blinding? If so, at which steps? If applicable, a statement that such methods were not taken and why. Have any data points or entire experiments, outliers, been removed from the analysis? If so, based on which criteria? Provide the full name of the statistical tests you have used. Don't just say we used a t-test, but rather, if applicable, we applied a two-tailed paired t-test. Or don't just say we used ANOVA, but if applicable, repeated measures ANOVA with Dunnett's multiple comparison tests. And name and full version number of the software used for any non-trivial analysis. The latter is relevant because sometimes published software has errors, which are then removed in later versions. This will allow readers to see whether the software you have applied may have contained such errors. Recommendation number 5, report in detail, and the buzzword here really is in detail, whether and how bad values or experiments were removed from analyses and graphs. As I talked about yesterday, removal of outliers can be legitimate or even necessary, but they can also lead to false positives, type 1 errors, and exaggerated results. One cause that may fool us are data underlying a log normal distribution. I'll show you an example of this. On the left panel, you see a number of data sets which look as having a few outlier data points. However, as soon as you log transform the data, you will see that all 5 data sets here have a perfectly symmetrical normal distribution. Outlier removal based on gut feeling can be highly biased. It should, if possible, be based on pre-specified rules, or, if that cannot be done, by a person blinded to group allocation, as that person does not have the same bias as you have. Explain in your manuscript why and how outlier removal was done. Recommendation number 6. Report confidence intervals to show how large a difference or ratio was. The confidence interval is more informative than a p-value because it also shows whether the lower end is still of biologically meaningful magnitude. In the figure here, you see 2 fake datasets. Both have exactly the same effect size. However, the one shown in blue has a small variability and then a low p-value, whereas the other has a larger variability and that leads to a higher p-value. If you just report the p-value, it would look like the 2 studies having vastly different outcomes. In this case, the opposite is true. They both have the same outcome. However, with low variability, it does reach statistical significance. With the larger variability in the red data set, it does not. Recommendation number 7, again, report p-values sparingly. A p-value answers the question, what is the probability to find this or a larger effect if the null hypothesis is true? In contrast to a frequent misconception, it does not answer the question, what is the probability that the effect is false? The p-value can be small, but the effect size be of little biological relevance, or vice versa. And as I showed you yesterday, p-values are highly fickle, and this slide is just showing you to remind you of the example when I showed you that 20 students from a statistics course picked random numbers from a database of real data, and they got vastly different group means and differences between groups, and accordingly vastly different p-values, in some cases very, very small, even though the difference was not real. Which brings me to the question, what is really a p-value? In any given data set, a fixed mathematical relationship exists between variability, for example, expressed as standard deviation within the tested sample, the observed or desired effect size, the sample size, and the p-value. As soon as one of the four changes, the others will change as well. We can apply this fixed mathematical relationship in data analysis. We know sample size, how many experiments did we do, and which variability and effect size were observed. And based on these three, we can calculate the p-value. We can also use this relationship in forward mode in study planning. We know or assume variability, the smallest effect size we care about, and the desired p-values threshold. And then we use those to calculate sample size in a power calculation. So what drives the low p-value? I have provided you here on this slide with a couple of fake data. So you have a difference between the means of about 50% and a standard deviation of only 5%. Mind you, in more than 30 years in science, I very, very rarely came across a test that consistently has a standard deviation of only 5%. So this is a really low variability. And with this low variability and a sample size of 5, we got a p-value of less than 0.0001. Well, if I just change variability a bit, the same difference between the groups, the same sample size, only the standard deviation now is about 20%, which is not really that high. It's something I encounter in many of the assay systems I look at. And suddenly, I get a p-value of 0.06. Well, that's bad news, because with a 50% difference and a p-value of 0.06, I can neither claim that I didn't see a difference, nor can I claim that I did see a difference. So what does this not significant mean? No statistical test on the planet can prove the null hypothesis. If the null hypothesis could not be rejected, it means just that. Possible explanations include there is no difference, the effect size was too small, the sample size too small, the variability too large, or it's a type 2 error, a false negative. So the bottom line of this is absence of proof does not equal proof of absence. Beware of false conclusions. And you have seen this graph from the Unpaired paper published in Nature last year already. Let me come to the concept of the false discovery rate, a term that was coined by David Cologne from from Cambridge. And he illustrates this with the following example. Let's assume 1,000 scientists run an experiment. And the prior probability that the outcome is positive, let's assume to be 10%, which means a real effect should occur in 10% of the 1,000 experiments, which is 100 experiments. At a power of 0.8, you should get 80 positive tests, true positive tests. However, you will also get 20 negative tests, which in this case would be false negative tests. As I showed you yesterday, 80% power is vastly over-optimistic, as less than 1 in 5 studies in experimental biomedicine has that much power. However, if the prior probability was 10%, out of the 1,000 tests, 900 in reality should come out negative. At a significance level of 0.05, you will get 5% positive tests based on chance alone out of these 900, which are 45. So in total, these 1,000 scientists will obtain 125 positive statistical tests. However, 45 of those are false positive, yielding a false discovery rate of 36%. And as I said, that's an optimistic setting. It assumes they all had a power of 80%, which is unrealistic. It assumes no biases were there, no p-hacking, no HARKing, none of this. So in reality, false discovery rates greater than 36% are very, very common. What drives the high false discovery rate? A key point is low prior probability that the hypothesis was true. So, in other words, how unexpected was the exciting finding? You could turn this around and say, the more exciting an observation is that you made, the greater the chance it's actually untrue. And that is a key reason why there is a strong recommendation to differentiate exploratory versus hypothesis testing studies. A low statistical alpha, also known as the p-value, low statistical power. In the words of David Colquhoun, a p-value around 0.05 means nothing more than worth another look. If you want to avoid making a fool of yourself very often, do not regard anything greater than p smaller 0.001 as a demonstration that you've discovered something. Of course, to be taken with a grain of salt. The 0.05 threshold, also known as the statistical alpha, is arbitrary and used for no reason except tradition. What may in many cases be more informative to consider the consequences of a false positive or a false negative and adjust the threshold p-value accordingly. Most interpretations and decisions are based on multiple and often complex sources of evidence. Recommendation number 9. Beware of the word significant. Significant has two distinct meanings in English, but also in many other languages. In plain language, it means suggestive, important, or worthy of attention. In statistics, however, it means that the observed p-value was smaller than the preset statistical alpha. As I told you, an observed effect size can be important in magnitude but have a large p-value, whereas an observed effect can have a small p-value but the effect is too small to be relevant. And therefore the word significant is ambiguous. In science, we should not try, or we should try to be not ambiguous. And therefore, the word significant should probably be replaced by what you really mean, either important or worthy of attention, for example, or by the real p-value that you measured. As I already showed you, if the p-value is greater than 0.05, it just means that the null hypothesis was not rejected. Not more, not less. Recommendation number 10. Avoid bar graphs. Bar graphs show only two values, a mean and an error bar, but that can be misleading, as multiple types of data can hide behind the same bar graph. And Tracy Weisgerber from the Mayo Clinic was the first to bring this to our attention. On the left, you see a typical bar graph. And then the four data sets right to that all could explain these bar graphs. But of course, they represent vastly different things. In panel B, you see symmetric distributions in both groups, and that's kind of what you expect when you see the bar graph. However, it could also be two groups that are very similar, but one has an outlier. They could have bimodal distribution or highly unequal n. So for these four data sets, yielding the same bar graph, depending what is the real data behind it, you could get quite different p-values ranging from 0.026 to 0.1. And the bar graph really hides that. What are the alternatives? If you have medium to large data sets, for medium data sets, the standard recommendation would be a box and whisker plot, where you see the mean, as part of the box, the difference between the upper and lower quartile, and then as the end of the error bar, the smallest and the largest value being measured. A scatter plot with large data set can get messy because you can no longer really see individual data points. And the more recent alternative to that is the so-called violin plot, which shows you the full range of the data and how many data points were at a given value, and also the upper and the lower quartile boundary. If you have smaller data set, as typical in experimental biomedicine, and here an example from one of my PhD students from Indonesia, Ayu Fraser, at the left, you see the scatter plot. On the right, you see in the upper left panel the bar graph that we reported 14 years ago in the published paper. And if you look at that bar graph, you see it's all about, in the old rats, the effect is half as in the young rats, and the error bar is small. And the psychological perception is, oh, this is a really meaningful difference. If you look at the raw data on the very left, well, the difference is there, but the two groups really do overlap quite a bit. If you switch to standard deviation, you already are less certain how relevant this is, because that the two groups overlap becomes more evident. And if you show confidence intervals or not assuming normal distribution, interquartile ranges, in all those cases, error bars become larger and making it more realistic to grasp how much the two data sets really differ. Therefore, recommendation number 11, and that's the last recommendation I'll be talking about today, do not show SE or SEM error bars. SE error bars are most likely so popular because they are smaller than others that make difference look more important than they probably are. But other than this, there's also sound theoretical reasoning why not to use SE or SEM error bars. Standard error is an indication of precision, not of variability. However, if there is a good reason to show precision, the confidence interval is more informative. If you want to show variability, you should use standard deviation, or when not assuming a normal distribution, the interquartile range. These were the 11 recommendations I wanted to talk about this afternoon. I will now show you 4 examples how that may look. So example number 1 is a data set you've just seen, where the biology is we compared maximum relaxation of the urinary bladder strips obtained from young and old rats by norepinephrine. The left half of the figure shows the data that actually would be sufficient, but the results are more complete by showing on the right half the 90% confidence interval for the difference between the two groups. How could you describe that in the paper? And I'm now giving you a possible wording. In methods, relaxation was expressed as percent, with 0% being defined as force immediately prior to start of adding norepinephrine and 100% as a force of 0 millinewton. Assuming sampling from a Gaussian distribution, maximum relaxation by norepinephrine in the two groups was compared by an unpaired two-tailed t-test. In results, you could say the mean maximum relaxation provoked by norepinephrine was 25 percentage points, 90% confidence interval 9 to 38%, larger as absolute difference in old rats than in young rats, and then provide the p-value. And a wording for the figure legend with high granularity would be each symbol shows data from an individual rat. The lines show group means. The analysis steps had been decided before we looked at the data. The right panel shows the difference between mean and its 95% confidence interval. The sample size were unequal at the beginning of the experiment due to availability, and sample sizes did not change during the experiment. Another example. One of my PhD students from Greece, Katerina Okiki, measured cyclic AMP accumulation in CHO cells stably transfected with human beta-3 adrenoceptors that were pre-treated for 24 hours with 10 micromolar isoproterenol or vehicle, and then re-challenged with freshly added isoproterenol. Again, the left panel would be sufficient, but the right panel provides relevant additional information. How could such a description look like? In methods, the logarithm of the Emax of freshly added isoproterenol, as calculated from a full concentration response curve, was determined in each experiment from cells pre-treated with isoproterenol or vehicle. The two sets of Emax values were compared with a two-tailed ratio paired t-test, equivalent to a paired t-test on the log of Emax. Possible wording for results: pre-treating with isoproterenol substantially reduced maximum isoproterenol stimulated cyclic AMP accumulation. The geometric mean of the ratio of Emax values pre-treated with isoproterenol divided by control was 0.26, 90% confidence interval 0.16 to 0.43, p-value of 0.002 in a two-tailed ratio paired t-test. Possible wording for the figure legend: each symbol shows the Emax of isoproterenol stimulated cyclic AMP accumulation from an individual experiment. Data points from the same experiment pre-treated with isoproterenol versus pre-treated with vehicle are connected by a line. Sample size had been set prior to the experiment based on previous experience with this assay. Each symbol shows the ratio from an individual experiment. The error bar shows the geometric mean and its 95% confidence interval. Example 3. What we've done here is a comparison again of rat bladder relaxation by isoproterenol after a 6-hour pre-treatment with vehicle or 10 micromolar of various agonists. How can we describe that in methods? Relaxation with each experiment was expressed as percent, with 0% being the force immediately prior to start of adding isoproterenol and 100% lack of contractile force. Measured tension, 0 millinewton. Concentration response curves were fit to the data of each experiment based on the equation to determine the top maximum effect, Emax, and log EC50 with bottom constrained to equal 0. Note that this equation does not include a slope factor, which is effectively equal to 1. Unweighted nonlinear regression was performed by PRISM, including the software version number. Emax and minus log EC50 values from tissue with pretreatment with a beta agonist were compared to those with preparations pretreated with vehicle by one-way analysis of variance, followed by Dunnett's multiple comparing tests and reporting of multiplicity-adjusted p-values and confidence intervals. As sample sizes had been adapted during the experiment, the p-values and confidence intervals should be considered descriptive and not as hypothesis testing. For results, freshly added isoproterenol was similarly potent in bladder strips pre-treated with vehicle or any of the beta adrenergic agonists. The Emax of freshly added isoproterenol was reduced by pre-treatment with isoproterenol, mean difference 22 percentage points, or phentoterol, mean difference 24 percentage points, but less so by pretreatment with CL316243, 11, or mirabegron, 14 percentage points. For the legend, the left panel shows Emax for individual rats and the lines show means of each group. The right panel shows the mean difference between treatments with multiplicity-adjusted 95% confidence intervals. All analysis steps had been decided before we looked at the data, but the sample size had been adapted during the course of the experiments. So, let me conclude with some take-home messages. The proposed recommendations were developed for pharmacology journals, but are applicable to most areas of non-clinical biomedical research. Key recommendations are: report with sufficient granularity to allow independent replication in text and figures. And you've seen from the examples I presented to you that this will result in considerably more extensive wording than you probably are used from reading papers. However, this is necessary to really tell readers what you have done. Distinguish between hypothesis testing and exploratory studies, the latter leading to a descriptive statistical analysis, if at all. Finally, focus on effect sizes and their confidence intervals. And with that, I thank you for your attention, and may the force be with you.